So question 22 is kind of like a number theory question. So we have want to know for how many positive integers n less than or equal to 24 is n factorial evenly divisible by 1 plus 2 plus dot 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 plus all the way up to n. So the first step is to get a closed formula for 1 plus 2 plus dot 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 plus n. So this is like what we call the triangular numbers. So this is well known to equal like n times n plus 1 over 2. And in case if you don't know like why this is true, like just if you're wondering like why this is true, like a quick proof you can say is like if you let s equal 1 plus 2 plus dot 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 plus n minus 1 all the way up to n. So this is a sum we're interested in. We can kind of like reverse the sum, right? Write it in reverse, but it's still the same sum. So I can write this as n plus n minus 1 plus dot 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 plus 2 plus 1, right? I just flipped the entire expression over. Nothing wrong with that. So I can add these two expressions together, and on the left side I get 2s. On the right side, 1 and n, that gives n plus 1. 2 and n minus 1, that also gives n plus 1. And you notice that any pair of these, the sum is always n plus 1, right? These two also pair to n plus 1, and these two also pair to n plus 1. So and you have n of these numbers, because you go from 1 through n. So this equals n times n plus 1. So from there you get s is n times n plus 1 over 2. So that's like a quick proof on why the sum of the first n numbers is n times n plus 1 over 2, in case you weren't familiar with that formula before. But that's like the first step to the problem. So we want n factorial to be evenly divisible by that number. So that essentially says that if we take n factorial and we divide by n times n plus 1 over 2, this has to be like an integer, right? So if n factorial evenly divisible by n times n plus 1 over 2, then this division must be an integer. So I can write n factorial. So I can first move this 2 to the top, right? So 2 goes to the numerator. N factorial you can write as n times n minus 1 factorial. And the bottom is n times n plus 1. So then from there you get 2 times n minus 1 factorial divided by n plus 1. So we want this to be an integer. So from here you kind of have to use your common sense. You have to use your logic skills. Because notice that n minus 1 factorial, remember that by definition, n minus 1 factorial is the product of all the numbers from 1 to n minus 1. So this is essentially equal to 1 times, and then 1 times 2 times 3 times 4 times dot 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 times n minus 1, all of those numbers divided by n plus 1. So the idea is if n plus 1 is a composite number, so if n plus 1 is not a prime number, then you can always write n plus 1 as the product of two smaller numbers. And those two smaller numbers, you can cancel with the numerator. So for example, what I mean is, for example, if n plus 1, if you said n was 7 or something, or let's say n was 5, then if you substitute n equals 5 into the expression, you get 2 times 1 times 2 times 3 times 4 divided by 6. So if this denominator is not a prime number, then you can always write it as the product of two smaller numbers. So you can write 6 as, in this case, 6 as 2 times 3, which is guaranteed to cancel with terms in the numerator here. It's we can cancel these 2 times 3 with that 2 times 3. So the idea is if n plus 1 is not prime, then we can always cancel it with stuff in the numerator. But that doesn't necessarily mean if n plus 1 is prime, then it'll always not work. Because you just have to kind of consider the special case. Notice if n equals 1, then you would have 2 times 0 factorial divided by 2. And this turns out to be 1. So this is an integer, even though this denominator here is prime. 2 is a prime number. That's kind of an exception. All other prime numbers would fail. For example, if we had for example, to make it more concrete, right? If n was 6, so if n was 6, plugging that into the expression, you get 2 times 1 times 2 times 3 times 4 times 5, and the denominator is 7, because clearly the denominator here is prime, is 7, so you can't split it into smaller numbers. And if you can't split it into smaller numbers, there's nothing in the numerator that has a 7 in it, so you can't cancel it with the denominator. So which is why, assuming bigger than 2 in this case, the only reason we were able to cancel it in this case is because we had this extra factor of 2 sitting out here, so we were able to cancel that. But with all other prime numbers greater than 2, we're not able to like cancel out the numbers from the denominator from the numerator. So that tells us that whenever n plus 1 is an odd prime number, it doesn't work. So if n plus 1 is like 3 or 5 or 7 or 11 or 13, 17, 19, or 23, right? Remember the original question said that, you know, n had to be less than or equal to 24. So like n is less than or equal to 24. So that means we go up to 23 and we find that there are 8 prime numbers here. So we find that 8 of these numbers of n don't work. So 8 of these numbers don't result in an integer division. But the original question asked how many are divisible. So we want to like subtract from the total. So in total, there were 24 numbers from 1 through 24. 8 of them don't work. So minus 8. And the answer would be like 16. So that would be the answer, which is choice C. So basically the idea was we first quickly derived the sum of the numbers from 1 through n. This is a very important thing to like memorize and like know very well. So you might as well just like remember this formula and know how to use it, because you know during the test you don't have time to derive a formula. So it's probably a good idea to like memorize this formula. But the idea to derive it was basically you write the numbers from 1 through n, and then you write it from reverse, and then you add the two equations like this. And the proof is pretty straightforward. It's pretty cool. So it's like that. And then we basically needed n factorial divided by that expression to be an integer. So we simplified it, and we got 2 times n minus 1 factorial over n plus 1. And we noticed that in order for that to be not an integer, we would need n plus 1 to be an odd prime number. So we found that there were 8 of those numbers, which we listed here. N plus 1 can be any of these prime numbers. But we want this counts the number that don't work. We want to count the number of numbers that do work. So we would do 24 minus 8, which is 16. So yeah, that's how you would do that problem.